Swayam Prabha. Digital India. Educated India.
In our previous lecture, we have seen that for a single cylinder engine, the turning moment on the crankshaft varies quite substantially. That is, if we plot the turning moment for a whole cycle, taking a 4-stroke cycle engine, so we have seen that it will be something like this, whose average value will be so this is the turning moment m, and this is the average value of this. How to find out? First, let us find out this is one cycle. And in this particular case, the crank rotation to complete one cycle will be 2 rotations, that is 2, that is angle theta will go to an angle 4 pi. Now, the total work done by the engine in one cycle is what? Because if it goes by, it rotates, the crankshaft is rotated by an infinitesimal angle d theta when turning moment on it is m, then the work done by the engine is m to d theta. So therefore, in whole cycle, the total amount of energy which is generated can be written as in this particular case, that means for 2-stroke cycle, E will be equal to 0 to 2 pi m d theta, and for 4-stroke cycle engine, energy will be so this is the amount of energy generated in every cycle. And obviously, in steady state, we assume the same amount of energy is utilized, so that there is no accumulation of energy in the engine continuously changing its speed. In case of starting, either it increases, or when it is less than the power utilized at the output end, then it will gradually go down. So in steady state operation, what we have, the resisting torque, which is constant, we have assumed in this particular situation, it must be equal to the value such a way that total work consumed by the load is same as the total energy produced in every cycle. So the load m is same as m average, which is nothing but the energy produced per cycle divided by 4 pi in case of 4-stroke cycles as shown here. That means we can write it like this. So once we know the turning moment diagram, it is possible for us to find out the average moment, or which happens to be the load or the resisting moment. Now we find that if we draw this resistance or resisting moment, then I think we find that if some places this is above this resistance, in some cases driving torque is less than. So here what will happen? Energy will be added to the system, so the kinetic energy will go up till point B, after which the driving moment becomes less than the resisting moment. So energy is depleted and kinetic energy goes down up to a point C, where again your driving moment becomes more. That means it starts accelerating the system, adding energy till the point say D, where again the driving moment becomes less than the resistance, and so energy is depleted, reducing the speed. Again it goes back to point A. So here we find that energy at A is say EA. Energy means obviously mechanical energy of the system, that is the kinetic energy. So at point B, the energy will be whatever energy we had at point A plus the energy added this is the amount of energy which is added in that first lobe, which is indicated as plus. Similarly, energy at point C will be E of B plus theta B to theta C m minus mr d theta. But remember, m minus mr is a negative quantity, and so actually it is going to be a negative quantity. Similarly, at point ED, the energy ED is energy at point C plus and we then finally come back to A, which is again so this is just an example. It can have many more lobes and different, because remember this is a case of a single cylinder engine. If we have more than one cylinder, then what will happen? The turning moment diagram of one cylinder and the turning moment diagram of the other cylinder, they will have to be superimposed with suitable lag. In case of two-stroke or two engines, obviously they will be separated by 2 pi angle, and so then the final turning moment will be a superimposition of data. If there are more number of cylinders, then the turning moment of each and every cylinder will have to be added by suitably phasing them, and the final turning moment diagram can be having many more loops than what we have here with only one cylinder. Now let E1 be the maximum energy. Amongst all this, of course, you have to see that energy can be maximum in any of these points, here or here and so on. Similarly, energy can be minimum also, either here or here, like that. So therefore, one of these must be the highest and one of these will be the lowest. It cannot be anywhere in between, and E2 be the minimum. The corresponding angles be theta 1 and theta 2. So, what will be the difference between the maximum kinetic energy of the system and the minimum kinetic energy? What we call that maximum energy, kinetic energy fluctuation, that is the difference between the maximum and the minimum values of the kinetic energy during the whole cycle, will be nothing but now the quantity, in this maximum fluctuation, that means the difference between the maximum and minimum values of the kinetic energy, what we call delta Ke max. If we divide this by the energy input per cycle as defined by this is called coefficient of energy fluctuation. Now, what is this fluctuation, this maximum and minimum kinetic energy? Now, obviously, we can always write, if let I be the equivalent moment of inertia of the whole system assumed to be mounted on the crankshaft. So, at any instant, the kinetic energy of the whole system can be now represented by this quantity. So, E max is nothing but the maximum kinetic energy of the whole system, that is half I omega max square, or omega max is the maximum speed of the crankshaft. Similarly, E mean will be half I omega mean square. So, therefore, delta Ke max is nothing but half I omega max square it is nothing but the difference between the maximum and minimum kinetic energy. This can be written in this form, I into omega max plus omega mean by 2 into omega max minus omega mean. Now, what we can do, there is a fluctuation of speed obviously. what we can do, this omega max plus omega mean, their average in most cases, since the difference is very small, can be considered to be the omega average. So this can be approximately written as omega average, or the average running speed of the engine. So we can write this as I omega average square into omega max minus omega mean by omega average, and this is I where the maximum variation in the speed divided by the average speed is called the coefficient of fluctuation of speed. This is an important parameter which has to be prescribed depending on the situation or the kind of machine we are driving with the engine. So therefore, we find that if Ks is prescribed, running speed is known, which is the design speed, turning moment diagram is known, then in the steady state we can find out what must be the equivalent moment of inertia of the whole system. Generally, what is done, that the system's inertia is not enough, and to provide or to make the system running smoothly, we increase the value of I substantially. How can it be done? The easiest way of doing it is that we attach a heavy wheel to the crankshaft. Normally that is called flywheel, because its function apparently is not seen very clearly, but what it does, it provides a substantial amount of magnitude to this moment of inertia attached to the crankshaft, and for a given fluctuation of energy, it produces much less fluctuation in the speed, or in other words, the engine runs smoothly. So in most cases you can say is approximately equal to the flywheel moment of inertia, because engines, connecting rod, etc., and the balancing masses which are added, they have inertia, but the real contribution to I comes from the flywheel which is attached to the connecting rod. And therefore, we can now find out that approximately we need a flywheel whose order of magnitude is found out from maximum fluctuation of energy divided by omega average square into coefficient of fluctuation. So this is the way or technique by which we can have very small fluctuation of speed by having very heavy flywheel. And therefore, as you have seen, in most engines we attached a heavy flywheel to the connecting rod. As I mentioned just now, that the value of Ks depends on the kind of situation or the kind of function we are achieving. So I will just give you some idea about the magnitude of Ks in various situations. This table shows the permissible recommended values of the coefficient of fluctuation of speed. In case of shearing machines, pumps, the accuracy required is much less, and value of Ks is in that range, 1 by 5 to 1 by 30. In machine tools of different types, textile machines and such types of situations, Ks can be permitted to be within 1 by 40 to 1 by 50. In case of electric generator or generating set, the recommended variation of speed has to be 0.01 to 1/3 of that, and automobiles or auto engines, the recommended value of Ks is this, and aircraft engines of course will have to be far more accurate, and there the speed fluctuation which is permitted is the minimum. Now let us consider just how to use this. One example let us solve. Let us take the case of an example of an engine. So the engine runs at RPM, 800 RPM. Permissible value of the fluctuation of speed is 2%, and the turning moment diagram has been given. The turning moment in Newton meters and theta in radians. This is one cycle. Now, here what has been done, this point A, this is point B, this is point C, point D, point E, F, G, H, which is same as A. Now, here of course you see that it is again becoming negative, that does not matter. So, here the area when you plot it both in centimeter and centimeter in this direction, this area is found to be minus 0.5 centimeter square. This is plus 1.2 centimeter square. This is minus 0.95 centimeter square. This is plus 1.45 centimeter square. This area is minus 0.85 centimeter square. This area is plus 0.71 centimeter square, and this is say minus 1.06 centimeter square. So we plot this. That means here actually we will find scale will be 1 centimeter is equal to 30 degrees, and here 1 centimeter will be equivalent to 7,000 Newton meter. That is the scale we have used, and using these scales, these are the areas we measure by planimeter. Next, what we do, let us find out what is the maximum kinetic energy and minimum kinetic energy as we have been doing. How do we do? We start with A, say energy at A point is EA, energy at point B is EA minus 0.5. We need not convert this centimeter square into energy now. We can do it at a final thing, because everywhere if we just keep on in terms of the area, we will be able to identify the maximum and minimum, and then we will convert to the real energy unit. So the energy at this location is EA minus equivalent of energy, which is this. EC will be EB plus 1.2, which is effectively EA plus 0.7. E at D will be E at C minus 0.95, which means it will be E at A minus 0.25. E at E is E at D plus 1.45, which is same as EA plus 1.2. E at point F is equal to E at point E minus 0.85, which is same as EA plus 0.35. And E at G is E at F plus 0.71, which is equal to E at A plus 1.06, and E at H is equal to E at G minus 1.06. So we come back to a point at point H, the energy should be equal to EA. Now let us see out of this which is the maximum and which is the minimum. So it is not difficult to identify the maximum and minimum energy locations. Say we can compare all the values EA, this, we find that this is E maximum and we can find this as the E minimum. So the maximum fluctuation of energy which is nothing but E max minus E min, which is equal to or equivalent to rather we can say (1.7 centimeters). Now, how much 1 centimeter square represent? Now, torque into theta, torque in Newton meter into theta in radians is joule. So, 1 centimeter square is equivalent to 7,000, and 1 centimeter is 30 degrees, in radians it is pi by 6, so many joule, which is 3, 6, 7, 0. This is the scale. So here if you multiply by this, this is in joules, it is which is equal to 6,240 joules. Now our Ks has been specified as 0.02 and omega average, which you should be able to find out from this 800 RPM, which is 800 into 2 pi by 60 radian per second, which is 33.8 radian. So therefore, we utilize the formula derived that moment of inertia of the flywheel will be approximately equal to, neglecting the inertia of the other parts of the machine or the engine,